What if I told you that gravity works as nature's magnifying glass, creating multiple apparent images of the same object, and that what we see in the night sky isn't a true representation of our universe? Well, this phenomenon that keeps playing tricks on us is called gravitational lensing. To comprehend gravitational lensing, we first need to understand gravity. But what's gravity? Well, it's a consequence of the distortion of space-time. Massive objects create distortion in space the same way a bowling ball creates a distortion if you put it on a trampoline. On the other hand, light, which has no mass, follows those distortions. So when space is curved, light goes along these curves. So if this curved piece of glass can form a lens when it bends the light that goes through it, don't you think that a curved piece of space would do the same? Take for example, a massive object like a galaxy that would act as a lens between a distant light source and ourselves. This galaxy's gravitational force is so huge that it will cause the distortion of the surrounding space. Therefore, the light emitted by a distant source, such as a quasar, will deflect and form one or multiple apparent locations of the source. The lenses aren't just magnifying objects in the background, since not all lenses are perfectly shaped to do what a normal lens would. Some would be like funhouse mirrors. For example, astronomers witnessed an Einstein cross, which is 4 images of the same object arranged perpendicular to each other around the lens. We also got images of an Einstein ring, which we would get when the lens, the light source, and the observer are in perfect symmetry. But it doesn't stop here. Gravitational lensing enables us to discover the characteristics of dark matter. Since dark matter doesn't interact with electromagnetic force, therefore it neither emits nor reflects light, but luckily it does interact with gravity. Thus, it deflects the incoming light and acts as a gravitational lens. The distorted image of the object we show as a distribution of mass along the light's path. So all we have to do now is find the mass of all visible foreground objects, and what is left is presumed to be dark matter. This phenomenon also helps us locate exoplanets, since the light coming from the source will increase twice, not just once, in the presence of an orbiting planet around the lens. And wait, there's another trick. Gravitational lensing allows us to explore galaxies formed in the early universe, so we can say it can work as an enormous time machine. And who knows what other trick it might be also hiding away from us. Thanks for watching.